please have a seat. All right, so let's start the afternoon session. So it's quite a pleasure to have Jake Abernathy as our next invited speaker. Jake is an assistant professor at Georgia Tech. Just before that, he started his faculty career at the University of Michigan. Jake did his PG at UC Berkeley. And one thing you might not know, but he's a street performer. So he knows about games, not only in mathematics, but also with people. And he's an expert on sequential prediction making, and more recently working on games. So it's quite a pleasure to have him hear him speak here.
Hi, thanks. The other thing you may not know about me is that I was recruited to grad school at Berkeley by none other than Simon right here, who sent me an email while I was visiting France. And convinced me to not go to Stanford, and I guess he won in that respect. I think at the time I was leaning towards Stanford, so thank you, Simon, for making the right decision for me. Sorry for those folks who went to Stanford for grad school. Thanks for having me. I'm going to talk today, the kind of more novel research stuff I'm going to discuss today is towards the end. And I should have mentioned a lot of that work is with some grad students, and so Kevin Lay is I believe here, maybe it's Kevin in the audience. And also Junkun Wang. Is Junkun in the audience? Junkun? He's not here. Okay, that's too bad. Can't get your own grad students come to your talks these days. And also Kfir Levy was involved in some of this work as well, Kfir Levy at ETH. So I just want to talk today about, over the last year or so, I've been thinking a lot about games and machine learning. And of course, if you think about computer science and game playing, it goes back a long time. People were very excited by the idea of computer algorithms playing games, and of course, chess was the one that folks that generated a lot of attention. That really goes back, I think, into like the '60s. People realized that you could use programs to try to solve chess, and of course, it wasn't until maybe the '90s or early 2000s that it was clear that computers were better. This talk is about 4 days out of date because I hear that there's new news about DeepMind and playing chess and AlphaZero, and I'm not going to talk about that, but I just want to talk a little bit about the viewpoint of game playing and how computers interact with. Oh, that's exciting! How computers and software interacts with. You can save that to like the punchline of the talk if you want, but. I'm not here. I didn't realize. If you told me I was here for a juggling show, you should have warned me in advance because I would have brought my equipment with me. My students who find this is an aside. My students who find out that I was a former professional juggler will often ask me to do a show, and I tell them I only do shows right before the course evals are due, which is going to happen soon. So I'm actually going to do a show for my students next week. Anyway, another story. Okay, so Monte Carlo tree search is like the kind of classic idea behind solving games, right? The standard thing you'd want to do to solve a game is to, you know that there's an optimal strategy. You have a way to win a game if there exists an action that you can choose such that for any action of the opponent, there exists an action that you can choose such that for any action of the opponent, and so on and so forth. You can recurse to the end state of the game, right? And you can win the game if there always exists some action you can always play that such that for any action the opponent plays and blah, 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 you have some recursive strategy that guarantees a winning state. Now, of course, you can't do that. I mean, the problem with solving games is that you can't simply recurse through the whole game because it's too large. And some of the tricks that people have used is to essentially try to estimate the likelihood at a given state without having to recurse any further. Can you estimate the likelihood at a given state? What's the probability you're going to win the game from there? I've done some work with Manfred, who's here, on thinking about that in terms of online learning and experts problems, which is cute. You can get optimal solutions in that setting. But this idea has, was very popular, and now there's, now you're even seeing deep learning being applied to chess. The key idea being that you can look at a board state and use some kind of statistical reasoning to figure out whether that state is good and whether you're going to be able to win from that state onwards. You can't do any recursion any further because you don't have the computational power, but you can come up with some fast estimate of the likelihood of being able to win given a board state. So, and of course, we now have AlphaZero, these new ideas where you can also use self-play to evaluate the quality of a board state. You can actually use like the previous version of your algorithm. the previous thing you've designed to evaluate the quality of the current state of the board. And of course, there's a lot of work on this, and also thinking about what the randomization policy should be. Of course, you should do some exploration, and I'm not going to get into this, but I do think this is like an interesting idea, and there's been a lot of recent work in this area. But the key takeaway from this framework, one that I really like, is that you basically have algorithms that do debugging on other algorithms. So, you think about algorithms have bugs, but we often design other algorithms to fix the bugs that we introduce in the design of our algorithms, and that applies to game theory too. What you're doing is you're designing, you have your previous version of your chess engine, and you're trying to beat that. And essentially, that chess engine is trying to find bugs in your current iteration of your chess engine, and you essentially have designed the checker. You're designing both the strategy and also the checker that makes sure that you're behaving well. And this idea seems to be quite popular, actually. If you think about it, this is being used in all kinds of frameworks, in all kinds of across computer science. IDEs, in some sense, they check for type errors and things like that. Whether you're using variables, unit testing frameworks, the unit testing philosophy is that you should essentially write what the code should not do or should and shouldn't do in advance, and then you write the code, right? Vulnerability scanning, having things that scan systems to find, possible vulnerabilities that hackers could take advantage. So this idea of having algorithms that you design kind of the algorithm that is the adversary, and you design the actual player itself, the thing that you're trying to have succeed. That exists in machine learning too, and people don't always realize this. And so I just want to remind people, folks who may or may not know this. Some folks may know this, most folks may not. But boosting actually was first designed really as a zero-sum game. And in fact, what you're doing is you're designing two algorithms in parallel. So in boosting, the standard idea behind boosting is you have a set of examples, XY pairs, and you assume that there is a quote-unquote adversary, although actually the adversary is the thing which is essentially helping the algorithm. It's this weak learning oracle. And the weak learning oracle guarantees that if you give some reweighting of your data set, there's always some weak learner that can be selected, some predictor that can be selected from this class of predictors that will do better than random, just like a little bit better than random, that will perform better than random. When I say random, I mean according to the distribution that was proposed to the weak learning oracle. So if you sample the example from this reweighted distribution with not necessarily 99% probability, but let's say 53% probability, you will predict correctly on that example. And the key idea behind boosting is that you can repeatedly use this adversary that's going to keep trying to beat your reweightings of your data set, combine the outputs of that adversary in some way to get a strong learner, one that does well on the original data set or on the original problem with high probability, right? Will be accurate with very high probability, not with 51 or 52% probability. So this was shown by Freund and Shapiro in 1996. I'm going to give a quick review of this. So the framework goes as follows. You initially start with a uniform distribution over your examples. You have a bag of predictors, which we're going to hold on to. It's a data structure. It's going to hold on to some bag of predictors. And in every round, well, first you update the weights. So you have these weights, WI, which we'll define in a moment. And you come up with a distribution based on these weights. You just normalize those weights. You query the weak learning oracle to find a predictor that does well in this reweighted data set. You insert that new predictor into your bag of predictors, and then you update the weights. How do you update the weights? You actually emphasize the examples on which you were incorrect. You actually increase the weight of the examples for which you were incorrect. And in the end, after several rounds of this process, you output essentially a weighted majority vote you could just do a majority vote for not the added boost version, but the boost by majority version. You just do a majority vote in these predictors that you've produced. Okay, so that's the template behind boosting. And it turns out you can actually think about boosting through the lens of the minimax theorem. The minimax theorem is the most important theorem, at least in my research. It's a very important theorem for lots of areas of computer science. And it's funny, I think when you see it written, especially if you're a graduate student, you've seen this for the first time. I recall seeing this for the first time and thinking, obviously this is true. It's symmetric, min, max, max, min, right? Min over x, max over y. Min over p, max over q of p transpose mq should be equal to max over q, min over p, p transpose mq. And it's not symmetric. It's actually, to be clear, one side is strictly, if you're the min player, you would strictly prefer to be on the right side of this equation. Or at least you should, if I were to ask you, would you rather you're going to play rock, paper, scissors. Would you rather not know your opponent's strategy or know your opponent's strategy? Clearly, you would rather know your opponent's strategy. That would be, if you're the min player, that means you'd want to be in the right-hand side of the equation. But it so happens that in equilibrium, you don't care. You could actually also be in the left-hand side of the equation, and it would be the exact same scenario for you. That's what the min-max theorem tells you. In some sense, the exciting part of the min-max theorem is the greater than or equal to sign, having that equality actually be a greater than or equal to. It's very surprising that it's true. So the min-max theorem goes back, obviously, a long time, almost 100 years. And the question is, how do you prove it? Well, there's lots of proofs of, this is basically proving strong duality of linear programming, effectively equivalent to that. How do you prove it? Well, first of all, before you actually prove that, let me just say, how does that relate to boosting? Well, it turns out you can set up a game in boosting. In boosting, you have this class of weak learners, and you have this class of examples. And I can write a matrix, Mij. Mij is the whether H, the jth weak predictor is predicting correctly on the ith example. And we can just write a plus or minus 1 matrix, a binary matrix like this, and we can imagine a game being played with this is the payoff matrix of that game. You have the row player and you have the column player, right? The row player is the I guess in this case the row player is the data points, and the column player are the weak learners. And on each round, you can imagine the two players continually updating their actions and maybe trying to beat the other player, right? That's the kind of key idea behind boosting. And it so happens that the minimax theorem guarantees that such a strong predictor exists. So it turns out just the fact that you can find a strong predictor that has basically perfect accuracy is guaranteed by the minimax theorem. The minimax theorem is what gives you the ability to find this strong predictor. Okay, so and it turns out it's just a duality. So if I don't have enough time to go through all the details, but the weak learning hypothesis is essentially the fact that there always exists a weak learner that can do well against every distribution. The dual of that statement is the strong learning hypothesis, that there exists a strong predictor that essentially has perfect accuracy, has a margin of 2 gamma on every example. Okay, so I don't have time to describe that in full detail, but you can see that that's written up in a number of different places. It's kind of a classical result about boosting. The question is, how do you find that strong predictor? So we're going to now shift gears and talk a little bit about regret minimization. Some of you folks, many of you folks probably know about this already, but let me just review it. The standard online convex optimization framework, which is a generalization of this early results in online learning, involves the following protocol. This may seem a little bit off base, but we'll come back to why this relates to game theory and boosting soon. You have a learner. The learner has a decision set K, some compact convex subset of Rn. On each round, the learner has to pick a point in that convex compact subset, xt, some point xt. The learner then receives a loss function, lt, and then the learner pays the cost of that choice. But in the end of the day, it's not the total cost that's paid. It's this thing called regret. And I'm sure if you've been hanging around NIPS for a while, you've heard the term regret before. It's the difference, on average, between what you earned, or what you lost, I should say, playing this game, versus what you could have lost if you had seen the loss functions in advance and had fixed yourself to a single strategy. That's the min over x in k of the sum of lt of x. So this is the regret of this of your decision process. And the goal here, we call this the average regret. The goal here is to find an algorithm that guarantees that the average regret vanishes. It goes to 0 or is less than or equal to 0. And it so happens that such algorithms exist. And in fact, if you had been attending CULT over the last 10 years, there have been many proposed algorithms for this. And it's been an area of active study. And it really has been, essentially this area has been worked out by now. We know all of the results, upper bounds, lower bounds, optimal algorithms, randomized algorithms, deterministic algorithms. There's still open questions, but many of the key ideas have been worked out. So it so happens that the existence, as soon as you construct a no-regret algorithm, you actually immediately have a proof of the min-max theorem. And it turns out it's a constructive proof. That's what's beautiful. It's a constructive proof of the min-max theorem. So I'm going to prove something a little bit harder than the min-max theorem. I'm going to prove that convex concave payoff functions essentially have a saddle point. So I'm going to, for any convex concave function g, so I'm not going to use x transpose my, which I was using before. We're going to define a game in terms of a payoff function, g of x comma y. So g is a payoff function. G is concave in x. It's convex in y. Sorry, it's convex in x, concave in y. And it so happens that the min-max theorem holds for this payoff function g. G of x comma y. You can make the same statement for this particular payoff function. Okay? So how do we prove that statement exists? Well, I'm going to prove the harder direction. So I'm going to prove the less than or equal to, that min over x max over y of g of x y is less than or equal to max over y min over x Did I get that right? Min. Yes, that's right. That's the harder direction. Okay. So what you do, the way you prove this theorem is it's very easy, actually. It's surprisingly easy. Both players are going to be choosing points from their decision sets, xt and yt. And each of them sees a sequence of loss functions. You have this payoff function, g. It has two inputs. How do I convert this two-input payoff function, g, into a sequence of loss functions? Well, I'm going to define it as follows. The payoff functions for the x player are g of dot comma y1, g of dot comma y2, g of dot comma y3. Those are the loss functions for the x player. And for the y player, it's minus g of x1 comma dot being the input to the loss function. G of minus x1 comma. So basically, you insert the other player's action and then leave your action, don't fill that in, and that's the function, that's the loss function, right? So I can define these two pairs of sequences of loss functions. Both players can use an online convex optimization strategy to solve this, to try to do well in this scenario. And it so happens that there's a very simple proof that this guarantees convergence to a minimax solution to this game. And the proof is really, I can put it on one slide. It's essentially the only one direction really matters because the other direction is symmetric. If you just analyze what happens along the way, what is the average payoff, let's say, to the x, or average loss to the x player? So it's the average payoff in this game, 1 over t, sum of the g of xt comma yt. If we just look at what that means, well, I'm just going to define lt of xt as the loss function for the x player, and it's defined in the previous slide. It's just, again, this is just by definition, the first equality. And I've defined average regret, r bar t, for the x player, to be the difference between the sum of the losses of the x player versus the sum of the losses for the best point in hindsight. So the second equality is just a definition of what I mean by r bar. It's just a definition of regret. And now I do only a couple of small, well, then I replace lt of x with just g of x comma yt, which is what that's the definition of lt. And now I'm going to, so I've now just dereferenced what lt means, and I do one simple thing, which is I apply Jensen's inequality. You'll notice that I have an average of g of x comma yt. This function g is concave in the y's, so I can take the average on the outside and put it on the inside and get an inequality. This is the only interesting part of the proof, actually. It's min over x now, g of x comma average of the y's. And it turns out I can replace the average of the y's, let's say, with the best y, max over y. And I end up getting this less than or equal to max y min x, g of x comma y plus regret. The key thing is that regret term is going to 0. That was the important detail, that I have a regret minimized algorithm, that regret's going to 0. The same argument applied to the y player. I get the same statement. I could go through the proof, but it's this identical proof. But you get a lower bound that this average of these g values is at least as big as min over x, max over y, g of x comma y, minus the regret for the y player. So if you combine the two statements, again, you just apply the exact same argument for both the x player and the y player. You combine them, and you get the following statement. Min x, max y, g of x y minus something going to 0 is less or equal to max y, min x, g of x y plus something going to 0. And the key thing is those regret terms are essentially it's some duality gap, but that's going to 0. So you can assume that that's going to vanish. So okay, so this is a cool trick. The nice thing about this trick is it's not really a proof. It's actually a construction. This proof gives you an algorithm. It turns out along the way what I showed is that the average of the x's and the average of the y's are near optimal solutions to this game. They're approximate saddle points to this game. If you take the average x and the average y, it's an approximate saddle point. And you can be guaranteed, based on the regret bound, how good of a saddle point they are. So this is a funky construction. I mean, so now think about what we just did. I just tried to prove the min-max theorem by saying take two online convex optimization algorithms with regret guarantees, play them against each other in this game repeatedly, have them try to do well, have them try to minimize regret. And if you look at the average iterates of these players, you're going to find that those average iterates are approximate solutions to the game. Somehow by having these algorithms compete with each other, without realizing it, they computed a solution to this game. That's very nice. And this is essentially what's happening in boosting. That is actually what's going on in boosting. That majority vote output classifier, that is the average of the iterates that were chosen along the way. The iterates were the weak learners. You essentially take an average of the weak learners and you output the average weak learner. That thing is going to do very well. It's going to be an approximate equilibrium to this game, approximate solution to this game, and that's essentially the core idea behind boosting. It's using online learning techniques to solve this thing framed as a game, and it gives you a constructive solution. Very nice. This is used in other places too. You can solve linear programs this way. I actually have students taking an exam right now where this is one of the questions we ask them: how do you solve linear programs using this trick? Teaching a graduate ML theory course right now. Generative modeling, essentially GANs, if you can analyze. I'm not going to. I have work on thinking about GANs through the lens of game theory and regret minimization. I'm not going to discuss that today. But also, you've seen work in differential privacy, constructing private databases using this exact same trick. It's a very common trick, very nice trick, and you'll see it all over the place. So I'm going to talk a little bit optimization now, and some work I've been doing with students on optimization. It's been a lot of fun. So I'm going to now switch gears and just think about what kinds of optimization algorithms exist. So before I do that, let me just mention that if you take this technique, so most of the regret bounds, the average regret guarantees you get, the standard regret guarantee you get, if you have no assumptions other than convexity or convex concave, or convex loss functions, you get regret guarantees that are on the order of 1 over t to the 1/2. It's somehow a fundamental barrier. You cannot beat regret bounds that have better scaling with the number of iterations of 1 over root t. I mean, statisticians like that 1 over root t because it feels like, if you're trying to estimate something, 1 over root t is often, the best you can do in many scenarios. But it turns out that has been some work recently, in the last 5 years or so, that showed that actually you can solve games faster than 1 over root t. If you use the reduction I just showed you, the trivial reduction is going to give you a 1 over root t guarantee. After t iterations of this procedure, you get a 1 over root t approximate solution to the game. It turns out if you're a little smarter, it's 1 over t. How is that? Let me give you a quick explanation for this. So the standard algorithm that people use, really maybe the most generic algorithm you can think of, is called follow the regularized leader. And what you're doing is on every round, you basically solve a regularized optimization problem. I guess here I'm using linear loss. So you solve like the sum of the losses up until now. This is like the minimizing the loss up until now plus the regularization. You can show this is very generic. This is a very generic algorithm, exponential weights, online gradient descent. They all fit into the framework of follow the regularized leader. Okay, that's the standard algorithm. That's the one that's actually only going to get you a 1 over root t rate, this type of algorithm. The bound for follow the regularized leader looks like this. Most of the time, people look at these two terms. You take 1 over eta times the regularizer value at the optimum point, plus eta times something that scales with t. You trade off t here, and you get a t here times eta plus a constant over eta. You trade that off, you're going to get a root t bound. So average regret would be 1 over root t. Now, people tend to ignore this term right here, this kind of variance term, because it ends up being typically less than this term. You don't worry about that. You just drop it and say it equals less than or equal to 0. Okay, we're going to need that in a moment, though. Now, if you use a slightly smarter algorithm, and I guess this goes back to Cheng et al. And was followed up and discovered that there was a connection with game theory by Rocklin Sridharan. If you do one thing which seems really silly, and the key idea is effectively you duplicate the last point. The key idea is simply take the original optimization we had before. This is the original optimization, and just duplicate the last term of that optimization. Just duplicate it. If you do that, you end up getting a slightly different algorithm. But if you use this algorithm instead of the original algorithm in your game playing scenario in the framework I just gave you, it turns out that the rate goes to 1 over t. And it's very subtle. It's a very surprising and very subtle result. Something cancels, and it's funny, and I remember hearing this. It was very surprising because you really feel like we know that 1 over root t is a lower bound for solving online learning problems. So how can you do better in games? Well, what's going on in games is that if you know your opponent is giving you slowly change, if you're both using online learning, you can kind of synchronize the players a little bit. You can kind of have them play in a way that's good for each other, right? And that's what's going on. This optimistic follow the regularized leader, this optimistic variant, it's synchronizing the players a little bit better. It's letting them take advantage of the fact that things are slowly changing. Because what really happens is in the regret bound, you get a regret bound that doesn't depend on the sum of the norms squared of the LTs, but some of the differences between the LT and LT minus 1. And that's the real benefit there. You also take advantage of this term too, but I won't get details there. So let me now switch gears, and I'm short on time, I think, so how much time do I have? So I'm going to try to get through and explain a couple of new ideas we've been working on. 10 minutes, thank you. So back to just simple vanilla optimization. Vanilla optimization, you'll see the connection to these game playing in a moment, but we want to solve minimum over x and k of f of x. I just want to minimize a function f of x. And standard methods use these iterative methods. You pick x1, x2, and you hope that finally f of xt is close to f of x star. You want to make that thing go to be epsilon or be head to 0. A standard reduction, you can reduce this problem to online convex optimization immediately. It's trivial. A trivial reduction to online convex optimization. In online convex optimization, you have a sequence of loss functions, and they change in every round. But this time, just don't change them. Just use the same loss function, f. F, the thing you're minimizing, just make that your loss function on every round. Apply your online convex optimization algorithm to the same loss function every round. The only thing that's different is you apply Jensen's inequality, or take the f of the average output of your online convex optimization algorithm. Here Jensen appears again. It turns out it's the exact same idea as before. And then you get this regret guarantee here, and you can show that basically f of x bar t, the average output of the algorithm, is close to f of x star plus a regret. And of course, 1 over root t, if you know nothing else other than the fact that the function is Lipschitz and convex, then this 1 over root t is actually the best you can do. That's well known. You can't beat the 1 over root t guarantee. And this is good. This gives you a nice simple algorithm. For online convex optimization, is actually a harder problem than minimizing a convex Lipschitz function. And you can use this trick. The problem with this trick is that we know you can do better. We know that 1 over root t is not the best algorithm for optimization in general. If you add one assumption, which is the function is smooth. Smooth functions are very common. We often deal with smooth functions. It's a very natural scenario. You have a smooth function. You can get rates like 1 over t, even 1 over t squared. In some cases, when you have strong convexity, you can get e to the minus t. Right? So somehow that 1 over root t is not very attractive anymore. And the trick I just showed you on the previous slide doesn't get these stronger rates. Okay, and I think it was believed that basically somehow like the tools that we develop in online convex optimization don't really apply to the sort of standard optimization settings if you want to get these faster rates. I'm going to tell you today that's not true. So give me a moment. We're going to have to go back to game theory. Okay, so just to define for you some of the algorithms that do better for optimization. This classic Frank-Wolf algorithm, which relies only on a linear optimization oracle on every round. On every round, you compute a gradient of an average iterate, then you take call linear optimization, you get the minimizer in your set, you average that back into your iterate, and so on and so forth. And that gives you a roughly 1 over t rate. Heavy ball algorithm, which is like gradient descent, but adds this like funky momentum term right here. That's also known to have a 1 over t rate for smooth functions, for minimizing smooth functions. And then, of course, there's the famous Nesterov acceleration, which somehow broke a barrier. People did not think you could get better than 1 over t. And it turns out you can get 1 over t squared when you have a smooth function. It's very surprising. It's an algorithm that has it's like you look at it and it doesn't make a lot of sense. You have your iterate zt, but you compute a wt, which is like a gradient descent step from zt. But then zt is not updated on z. It's always, I look at it, it's very unintuitive. Then you do this momentum thing here, but it's kind of gradient descent, it's kind of momentum. It's hard to interpret, but it's very simple. You can write it down very simply. It's a very simple description. And this algorithm for smooth functions has a 1 over t squared rate. It's faster than all the other algorithms I've shown you before. So what's going on? Okay, so this work that I've been doing with Kafir and Jun-Kun and Kevin is showing that basically you can show like a lot of these algorithms are actually just game playing. So Jun-Kun and I had this paper from last year at NIPS. We just pointed out as a simple observation that it turns out the Frank-Wolf algorithm actually can be viewed as the iterative updates of a two-player zero-sum game. And then in Cult more recently, and I guess in NIPS this year, it's no longer in submission, but in NIPS this year we showed that, so we had a faster algorithm from this Cult paper and this past Cult, and for Frank-Wolf algorithm. And then this year we showed that actually the Nesterov acceleration can be put into this framework as well. And it's cute. It's a very cute solution. Okay. So what's the idea? Well, first of all, if you don't know what Fenchel duality is, here is the definition. I don't want to go into too much depth, but you have a function, you have its conjugate, called the Fenchel conjugate not much time. Fenchel conjugate of a function f star of theta is just this thing. And it's nice, it turns out like the Fenchel conjugate gives you like the inverse, like you can think of mapping a function x to its gradient of f. The Fenchel conjugate is like the inverse map. The gradient of f star is actually, the gradient of f star of the gradient of f is just x, right? It's this nice inverse relationship there. Okay, Fenchel duality, it's a nice idea. Won't go into too much detail. Here's a no regret perspective on iterative optimization. What we had to do is define a game. I'm going to now go back to game theory. Define a game, g. I need a payoff function, g of xy. So g of xy is going to be f star of x minus x transpose y. Okay, so we're going to use a game defined this way. We use the Fenchel conjugate of the thing we're trying to optimize, minus an inner product between x and y. That's a two-player game. It's convex in x, it's concave in y, right? Okay, so if I can solve this game, it so happens, it's not very hard to show. If I can solve this game, I've actually solved the original optimization problem. Equilibrium solution to this game, if I have an approximate equilibrium to this game, I've approximately solved the original optimization problem, which is to minimize f. So even though the game involves the differential conjugate of f, solving this game solves the original objective. Okay, so what we need to do is just define a sequence of loss functions for both players. We're going to have two players. They're going to use an online learning strategy against each other. They're going to play this game. They're going to use some update rule. We'll look at that in a moment. And they're going to have a weight. There's one little thing is we're going to use weighted regret. So some rounds are going to be weighted differently. Usually use uniform weighting. Every round has the same value. But now we're going to have different weights for every round. And you're going to have them play against each other with this game that defines the payoffs. And in the end, you're going to output the average of the points x and average points y. It turns out you can throw away the y's. They don't use them anyway. It turns out you don't use them. In this case, actually use the y's, not the x's. Whoops. So you're going to play this game. You're going to take the weighted averages of the x's and the weighted averages of the y's. That's going to be the solution, the approximate solution of this game, which is going to solve the original optimization problem. Okay, so it turns out that what we showed last year is that the Frank-Wolf algorithm is the following. You can describe Frank-Wolf in exactly the following way. The y player is playing what's called follow the leader, which is classic simple optimization algorithm. It's very much like follow the regularized leader, but you don't regularize. And then the x player plays best response. It's not really an online learning algorithm, but it's a response algorithm. You can respond to the y player. Respond to the y player. So simple. If you just use those two strategies for both players, you end up observing that the algorithm you get from that is the Frank-Wolf algorithm. And not only that, the analysis we get gives you the rate, 1/t rate for Frank-Wolf. So I don't have time to show the details, but if you go through the paper, it's not very hard. You can show that you can reinterpret Frank-Wolf as simply solving this two-player zero-sum game by having one player use follow the leader and the other player use best response. So now I'm going to change only a couple of characters on this slide, and I'm going to say, actually, the heavy ball algorithm, if you've seen the heavy ball algorithm also fits in with this framework. Turns out, before I had follow the leader versus best response, right? That was before. Just replace best response with gradient descent, online gradient descent. If you replace best response with online gradient descent, you get the heavy ball algorithm. And it turns out the regret analysis shows you why exactly you get a 1/t rate for the heavy ball algorithm. And in this year's NIPS, we point out that actually, if you take the follow the leader algorithm here for this heavy ball framework and replace it with optimistic follow the leader, with this optimistic variant, where you essentially duplicate the last point, we call it optimistic FTL, and you use, again, gradient descent for the X player, it turns out that what you find out is that that is exactly Nesterov's accelerated gradient descent. That is what Nesterov's accelerated gradient descent is. It turns out that if you simply analyze what the average iterates that you're outputting, they evolve precisely according to the recursive definition of Nesterov's algorithm, and it's essentially a reinterpretation of that technique. And it's quite cool. And the way you can guarantee you can get that 1/t squared rate is very subtle. Something very subtle about this, about the analysis that surprises me even to this day. You can show that the regret of the y player ends up scaling as the differences between these x values squared, and that's a very natural bound. It's very easy to prove that. In terms of the regret of the x player, because the x player plays second, you get this negative term, which comes up in all of these analyses that give you faster rates for solving games. You get this negative term, which is the negative sum of the xt minus 1 squared. And it so happens that the negative term of the x regret, because you're adding the two regret values together, you can get cancellation. Somehow the y player's regret is going to get canceled by the x player's regret, assuming you choose these alphas, these weights correctly. What you need is essentially for these alphas, you need the following condition for the alphas: alpha t squared over at. So at is the sum of the weights up until now. Alpha t is the current weight. The current weight squared over the sum of the previous weights has to be bounded by a constant, let's say 2. What sequence generates that? Well, it's sequence alpha t equal to t. Alpha t equal t guarantees that alpha t squared over at is less or equal to 2. And if you just look at the analysis, it turns out you're going to find that with that weighted regret, you get a cancellation on the top, and you have 1 over a sub capital T in the bottom. That a sub capital T is 1/t squared, and that's where the t squared rate comes in. So I think I'm out of time, so I'm going to leave it at that and open the floor for questions.
All right, we have time for a question.
Can you handle constrained optimization?
I think we can. I mean, the answer to that's yes. But I think in this particular version, we did unconstrained.
Any other question? Raise your hand.
So I have a question about the last part. Is there any advantage of analyzing the convergence rate from a game theory perspective view?
Yeah, it's a good question. I mean, I don't have to repeat these questions, right? Because okay, yeah. Is there an advantage of the game theory interpretation? That's a good question. I mean, first of all, what it does do is it tells you that decoupling things can often give you some benefits. Like the interpretation of decoupling, you have like a primal player and a dual player. And what's nice is, and we've shown this in previous work, that like you can somehow tinker with what the X and Y players are doing. Like just change something small of what the Y player is doing, and you get a whole different algorithm. Or if we change the order, for example, we showed that in the Frank Wolf paper. So far, we haven't gotten any dramatically amazing new algorithms for optimization, but we've been able to tinker with things, and it makes it very simple because all you have to do is prove two regret bounds. The analysis says, if you can come up with two algorithms that have two nice regret bounds, that's all you have to do. That's all the analysis requires. And oftentimes, the standard analysis of accelerated gradient descent is quite complicated. It has a lot of you have to analyze a lot of recursive expressions, and those regret bounds don't involve that, right? They're in some sense much more straightforward in how you look at them. I mean, there are parameter tuning issues and things like that, but I don't know if I answered your question, but it's the best I can say.
Any other question?
The algorithm you propose, one is using this optimized version, the other uses gradient descent.
Yeah.
Does it make sense to use optimized version for both of them?
Yeah, it's interesting you asked that. That was the original way of solving a standard linear zero-sum game. They were using optimistic for both players. We were kind of excited when we found that Nesterov acceleration emerges from one player using optimistic and the other player not. And we haven't analyzed it any further than that. This is sort of recent research, so I haven't analyzed it any further to see I think if both players play optimistically, you still get the same rates. But we were kind of trying to draw the connection to Nesterov acceleration, where only one player uses this particular optimistic. But it's a good question.
Could you just give again the reference when you said everyday momentum and Nesterov can be seen the same?
The paper's called Acceleration. It's in NIPS now. Acceleration through optimistic, no regret dynamics. Yeah.
So you assume access to F star of X? So
Yeah, it turns out, good question. So did I need somehow you say, oh, wait a second, you're using the differential conjugate here. Yeah. Oh, wait, do I need the differential conjugate? Yeah, that's a common question. I should have clarified this. It turns out that I never actually use the differential conjugate directly. I only use follow the leader-like strategies on the differential conjugate function. If you think about what follow the leader is doing here, it is solving an argmax over y of this expression, and what that is doing is computing the gradient of f at the input x. So I avoid having to deal with the differential conjugate directly. Algorithmically, I'm only using the gradients of the function itself. So in some sense, this game is abstract. I'm writing it down, but I'm never actually having to compute any game values, which is maybe good or bad, but that's what's going on. Yeah.
All right, let's thank the speaker again. All right, so our next speaker will be Rehan from Mila, and this will be our third contributed talk, I think. And she will talk about negative momentum for improved game dynamics. So you might have heard Kostis talk about negative momentum, so I think here we'll see a more detailed perspective on this topic.
Thank you, Simon, for the presentation. So today I'm going to talk about our paper on negative momentum for improved game dynamics. This is a joint work with Gauthier, Mohamed, Remy, Gabrielle, and our supervisors, Simone and Yanis. First I'm going to talk about single objective optimization versus game optimization and see how single objective optimization is different and what are the problems that we have to tackle on game optimization. Then I'm going to talk about the effect of momentum on game optimization and see if momentum can help the dynamics or hurt the dynamics. Then then I'm going to talk about the simultaneous versus alternating updates that are used in games, and then our results on bilinear games and on GANs. So if I want to motivate you, this is a vector field of our in the space of parameters. So in single objective optimization, we have a well-behaved dynamics. But in multi-objective optimization, we might see rotational dynamics. So let's see why this happens. So in single objective optimization, where we have a smooth differentiable loss function L, and we want to minimize this loss with respect to the parameters, we basically apply gradient descent. We find the gradient vector field by taking the gradient of the loss with respect to the parameters, and find the next iterate. We can also look at gradient descent as an update operator, which basically means you take you give as an input to the update operator your current set of parameters, apply gradient descent, and you get your next set of parameters. So finding a stable fixed point for your update operator f is equivalent to finding a local minima using gradient descent. So let's see how these concepts convey to multi-objective optimization. So in multi-objective optimization, where, for example, you have two loss functions that you want to minimize, and you have two players with parameters phi and theta, the vector field is going to be a vector of the gradient of the losses with respect to the parameters. And the update operator is going to take as an input a vector of your parameters. So we're going to look for the stable fixed point of our update operator f. So how do we know that this update operator is actually convergent? So we need to look at the Jacobian of our update operator f. So if the spectral radius of the Jacobian of f is smaller than 1, then f is convergent. So the Jacobian of f depends on the learning rate and the Jacobian of the vector field. We already know that we need to optimize the learning rate, but for the vector field, the Jacobian of the vector field in single objective optimization is basically the Hessian, and we know that the Hessian is symmetric. So it has real eigenvalues, and this is a well-known dynamic. But in games where we have multi-objective optimization, the Jacobian of the vector field might not be symmetric, so we might have imaginary eigenvalues and observe rotational dynamics. So let's look at a very simple bilinear example where the loss is phi theta, and one player wants to minimize the loss and the other wants to maximize the loss. So the Jacobian of the vector field is basically this matrix 0, 1, minus 1, and 0. And if you recall, this is basically the rotation matrix. So the plot shows the vector field in the space of our parameters phi and theta, and the equilibrium is at the center. So if we start somewhere near the center, we're just going to see rotational dynamics around the center and never converging to it. So the rotational dynamics are caused by these imaginary eigenvalues. So that's why we might expect to see the same kind of behaviors in GANs, and that might be a reason why GANs are so hard to train. So now let's look at the effect of momentum on games. So one thing that motivated us to do this work was a recent trend that we observed in GANs. So before the birth of the GANs, where we had most of the single objective optimization, people used the momentum of 0.9. Then this value was reduced to 0.7 for conditional for CGAN and pyramid GAN. Then DC GAN and cyclic GAN and many other GANs use a momentum of 0.5. Then the famous WGAN and WGAN GP use a momentum of 0. And the spectral normalization GAN, which is the state-of-the-art, also use a momentum of 0. So we thought that this trend is not an accident, and that's why we looked into it and wanted to see if for some setting and some games, the optimal value of momentum is actually negative. So Let's start with to see the dynamics with momentum. So without momentum, we already saw this, that we had our update operator F. Here, this is just a rewritten form of this update operator that by doing a state augmentation, we're having the omega, and so by adding a momentum, we're basically adding this new term with a coefficient of beta and a history of our previous gradients. So the Jacobian of our fixed point operator is going to turn into this formulation. And in the paper, through theory, we showed that the eigenvalues of the Jacobian of F have these are two sets. The first set is basically the original eigenvalues minus a shift term, and this shift term depends on the value of momentum. And the second set is basically only dependent on the momentum. So if we set momentum to 0, you see that we only get the original eigenvalues without momentum. And if we apply momentum, we see the shift on the original eigenvalues and new sets of eigenvalues. So let's look at this simple plot, which shows the eigenvalues in the complex plane. So as I said, the theory told us that the eigenvalues of the Jacobian of F need to be inside the unit circle. So we want all the eigenvalues of the Jacobian of F to be inside this circle to be convergent. So these eigenvalues, mu, depend on the learning rate, and lambda, which are the eigenvalues of the vector field. So by changing by changing eta, the learning rate, we're going to have different magnitudes of mu, the eigenvalue. And the best learning rate is actually where we're closest to the center, and we're going to converge the fastest. So if we choose a very large learning rate, we're going to be outside this circle and diverge. But the best learning rate is actually where we're closest to the center. So let's see how this changes with momentum. So as I said, the eigenvalues is going to be shifted by using momentum. And in the paper, we showed that by using a slightly negative value of momentum, we'll be able to shift the original eigenvalues to the left. So by this shift, you're actually decreasing the spectral radius, and two new eigenvalues are also introduced. So by shifting these to the left, you will have a smaller spectral radius, and you'll be able to use a larger learning rate and converge faster. Or if you were outside this unit circle, these shift is going to help you to move inside the unit circle and converge. So now I'm going to talk about simultaneous versus alternating updates that are used in games. So when you have two set of players and they have two losses, there are two ways to update the parameters: simultaneously or alternating updates. So in simultaneous, you take the gradient of the loss with respect to both parameters at the same time and update both of them at the same time. But if you use alternating updates, you first take the gradient of the loss with respect to the first set of parameters, update those parameters, and then take the gradient with respect to the second set of parameters and update those. So in practice, alternating updates are widely used, and they significantly improve the dynamics, but there was no theory telling us why simultaneous updates don't work. So in the paper, we showed that in bilinear games with simultaneous updates, the spectral radius of the Jacobian of F is greater than 1. So that's why simultaneous updates don't work. Also, an intuitive way to think of it is that alternating updates take advantage of this fact that the parameters of the other player has already been updated, so they take the gradient in the next step. So this helps us to converge. So now I'm going to move to the bilinear games. So in the paper, we showed that in a bilinear game with simultaneous, with no momentum, we're going to slowly diverge away from the equilibrium. With alternating updates and no momentum, we're just rotating around the equilibrium in a bounded circle. But if we use alternating updates with negative momentum, a form of friction is added into the dynamics, which helps us to converge. We also optimized this numerically and tried different learning rates and momentum, and the plot shows the spectral radius of the Jacobian of f. So in order for us to be convergent, we need the radius to be smaller than 1, which should be shown in blue, and if we're larger than 1, it is shown in red. So as you can see, with simultaneous updates, there's no setting of momentum and learning rates with which we can converge in bilinear games. But with alternating updates and negative momentum, there is a sweet spot with different learning rates that we can actually converge, and the best setting is actually found with a negative momentum. So now I'm going to move to our results on the most popular games these days, which are the GANs. So the plot on the left shows a grid of the different values of momentum and learning rates that we tried, and the color shows the inception score. So the lighter the color, the better the inception score, and as you know, the inception score shows a higher inception score has better image quality. So this is an image generating task on CFAR 10, and the optimal value of momentum was actually in this task a negative value of -0.4. So you can see the generated samples on the right, and I just have to mention that these results are with saturating loss. So this plot is actually a very good summary of the bilinear case. So if you apply gradient descent with simultaneous, which is shown in beige, with no momentum, we're actually slowly diverging away from the equilibrium. If you use positive momentum, things are going to actually be worse, and we're going to diverge faster. If we use a negative momentum, things get slightly better, but we won't be able to converge anyways. If we use alternating updates, which are shown in olive, you can see that with no momentum, we're just going to rotate around the equilibrium, never converging or diverging. If we use positive momentum, we're going to diverge. But if we use negative momentum, a form of friction is added into the dynamics, and a force will help us to move towards the center and converge to the equilibrium. So all in all, the main messages that we wanted to say in the paper was that, first of all, momentum interferes with game dynamics, and tuning the momentum parameter is very important. There are settings in which non-standard values of momentum are optimum. For example, in state-of-the-art GANs, as I mentioned, the optimal value of momentum was 0, and in a set of games that we had in this paper, the optimal value of momentum was negative, and for GANs with saturating loss in the settings that we tried, the optimal value was also negative. So it's very important for the ML practitioners to try different values of momentum, even the non-standard ones. And I also just want to emphasize that we didn't introduce a new method. We just tried to give a better. We just tried to give this concept that negative momentum could also be valuable to use, and that's it. Thank you for listening. Our paper is on archive, and if you have questions, I'm also available in the poster session. And thank you again to my co-authors that are listed here.
All right, so we have time for a question. And by the way, while our pictures are up here, if in case you want to accuse us of nepotism, the decision for Orwell was made by the reviewers. We followed the reviewer decisions. All right, so in the back, I will run.
Thank you for the talk and great work. So, given that your takeaway message was that we should try non-standard values of momentum, what are the conditions under which the negative momentum that you analyzed aren't ideal?
I think the dynamics of games are very complicated. So in the settings that we tried, if you look at the paper, we introduced the types of games from adversarial to fully cooperative games. And we showed that negative momentum is actually works with more adversarial games, but not fully adversarial games. So, and also in the settings where we had like GANs with saturating loss, which was a zero-sum game, in that setting also negative momentum helped. But we tried like the usual loss that was used for GANs, which are the non-saturating loss. And in that setting, negative momentum was not the optimal value.
Interesting. All right, thank you very much.
No problem.
Any other question? Okay.
Thanks for the great talk. Have you looked at the effect of taking several steps when alternating, let's say, between the critic and the generator, for instance, in GANs? Because in practice, people would take like many steps for the critic and just one for the generator. So have you looked at the effect
Well,
of
we actually don't have like a theory for that. We tried to like optimize this, and the setting that we had in the paper that worked the best was that we did both of them the same. We update both of them the same time. So we don't have like theory for the GAN, which would tell us that you have to like update them differently, like update the discriminator differently. Oh, but there's one point that I have to mention is that for this setting, the saturating GAN, we tried negative momentum only on the generator and not on the discriminator. And the reason was that because, intuitively we thought that the discriminator was usually faster to learn. So, only on the discriminator, yeah. So the discriminator was usually faster to learn. So that's why we gave this form of friction only to the discriminator. And we use a momentum of 0.5, I think, for the generator.
Thanks.
Any last question? No? All right, so let's thank Rian again.
Thank you.
So we have now a 30 minutes coffee break, and then we'll get back at 3:30.